Okay, we're doing section 6.5, and that is on convolution. Convolution basically is how we go about multiplying Laplace transforms. We already know how to add them. If I took the Laplace transform of a sum of two functions, that's just the sum of their Laplace transforms. We use this extensively to solve our second-order differential equations. But if I have the Laplace transform of a product of two functions, that is not equal to the product of their Laplace transforms. So what is this equal to? Well, let me rewrite it. If it's Laplace transform of the function f of t, that's capital F of s. And if this is the Laplace transform of the function g, that's capital G of s. Well, together I'll say the product of these is equal to hs. So that will be what the product of their Laplace transforms is actually equal to. That makes ht equal to the inverse Laplace transform of hs. And in order to find what f and g are, we need to invent a new function. And that function is the convolution. We use an asterisk to represent it. So it's f convolute g. And what this represents is a special function. It's actually an integral from 0 to t of f of tau times g of t minus tau d tau. Tau then is just a placeholder variable used for the integral. F and g will still be functions of t, and when I take this integral, it will perform the convolution of f and g and produce h. Basically, though, we don't often need to do this. That is, we're not going to very often calculate the convolution of two functions in order to form a new function. Instead, because this is quite common in the subsidiary equation, we're going to have to figure out how to take the product of two Laplace transforms, pull it apart into the two Laplace transforms that represents a product of, and then figure out what f and g are, and then use those to calculate h. So we'll be calculating h not from f and g directly, but by knowing what hs is. Okay, well, let's take a look at that. First, though, let's talk about some properties of the convolution. You can kind of think of it as multiplication, and in many ways, it's very much like multiplication. Of course, f convolute g is the same as g convolute f. That is, it obeys the commutative property. F convolute g1 plus g2 equals f convolute g1 plus f convolute g2. So it obeys the distributive property. F convolute g, and then that product convolute k is equal to f convolute the product of g convolute k. So it obeys the associative property. The final one is f convolute 0 is equal to 0 convolute f, which is also 0. So convolute by 0 is 0. So far, the property of convolute, that is the operation, looks an awful lot like multiplication. But there are a couple of stark differences. F convolute 1 is almost never equal to f. It's possible with the choice of just the right f that f convolute 1 will be f, but that's not a general property. So there's no sort of identity property of convolution, okay? And f convolute f is not always greater than or equal to 0. And of course, when you square any real number or any real function, it should always produce positive numbers, as long as f isn't some imaginary number or imaginary function. But this isn't always true, so sometimes this will produce negative values, okay? So those are two properties of the convolute that definitely tell you that you're not in Kansas anymore. This is not regular multiplication. Okay, well, let's talk a little bit then about how we'll actually use convolution in order to solve our differential equations. It's frequently going to involve, let me get rid of all these properties. It's frequently going to involve solving a problem like this. Given h of s, find h of t. And the problem is hs is a composite. It's a product of two different Laplace transforms. And I can't find h of t by just breaking those apart and then undoing the Laplace transforms. That's not how h of t is defined in terms of h of s. So let me show you how you do it with an example. So here's a given h of t, or h of s. It's equal to 1 over s minus a quantity squared. Okay, if we check our table of Laplace transforms, 1 over s minus a is e to the at. So this is 1 over s minus a times 1 over s minus a. That means this is f and this is g. This is big F and this is big G. That tells me what little f and little g are. Little f is e to the at, and g is e to the at, because the product of f and g is 1 over s minus a and 1 over s minus a. So these are easily recognizable. I can figure out what f and g are because the Laplace transforms are still recognizable, and I know that the product of them will simply produce f and g. But the answer for little h, of course, is not equal to just the product of these. It's not going to be e to the 2at. Instead, I have to perform the integral from 0 to t of f of tau, and that's going to be e to the a tau, times g shifted, it'll be e to the a t minus tau, and then d tau. And this is a pretty easy integral to evaluate. E to the a tau, this is going to be e to the at minus a tau. So if I put them all with a single exponent, it's just going to be integral from 0 to t of e to the at times d tau. Well, e to the at, that's just a constant. It can come out. And the remaining integral is tau evaluated between t and 0. That's just t. So this is t e to the at. So you can see that ht didn't end up as the product of these two. It ended up as whatever the convolution did to them, so that t e to the at is really what ht is. And this is a really common practice once you learn about convolutions, and that is to take a product of Laplace transforms and then figure out what that product's non-Laplace transform function is. Now, we can actually build a rule out of this, and that is that if I wanted to take the Laplace transform of the product of t times e to the at, well, I already know the answer to that. The Laplace transform of h of t is h of s. So I know the answer is 1 over s minus a quantity squared.